Hello everyone, my name is Surya Prabhav Gurram. Me and my teammate Soumith Reddy Asani will be presenting our project, which is titled Comparative Evaluation of Index Recommendation Methods for PostgreSQL Workloads. This project was done for CS5513 Advanced Database Management Systems under Dr. Lee Gruenwald. This slide gives a brief overview of the presentation structure. Before discussing the algorithms, it is important to understand the actual database problem we are trying to solve. Indexes are one of the most important tools available to a database administrator, or DBA, for improving analytical query performance. A good index can transform a very expensive scan over millions of rows into a fast lookup operation. However, indexes are not always beneficial. A bad index consumes storage, slows down inserts and updates, increases maintenance overhead, and can even cause the query optimizer to choose worse execution plans. So the central problem becomes, given a workload and a storage budget, which indexes should we create to minimize total workload cost? This is called the index selection problem, and it is considered NP-hard, meaning there is no known efficient algorithm that always produces the globally optimal solution. This problem has been even more important recently because modern workloads contain thousands of attributes, extremely large tables, and tens of thousands of distinct queries. This scale is far beyond what human DBAs can tune manually. Traditional systems like Microsoft DTA were designed for much smaller search spaces and struggle with today's workloads. Because of this, researchers have explored machine learning, reinforcement learning, and now large language model based index advisors. However, one major issue in the literature is that many papers evaluate algorithms using only optimizer estimated cost reductions rather than actual measured query latency. That gap is exactly one of the motivations behind our project. This slide summarizes the main objective and contributions of our project. The primary goal of this project was to compare two different index recommendation methods on the same PostgreSQL TPC-H workload. The key methodological point is that after each algorithm produced its recommended indexes, we physically created those indexes inside PostgreSQL and measured the actual query execution latency. So our execution is based on real execution time, real query plans, and real index maintenance behavior, rather than the only optimizer estimated cost. The two algorithms we compared were first extend, which is a classic recursive greedy heuristic proposed in ICDE 2019 and later identified by the Magic Mirror study as one of the strongest classic baselines. Second, LLMIA, a modern LLM-based index advisor proposed in 2025, which uses in-context learning with GPT-4o Mini to recommend indexes. The major contribution of our work includes, first, we performed a fully reproducible end-to-end comparison on PostgreSQL 18.3 with TPC-H scale factor 1. Second, we documented the substitution from our originally proposed balance and swirl advices, including an exact technical reasons why they could not be reproduced in our environment. Third, we demonstrated both the strengths and weaknesses of automatic index advisors. For example, both advisors rescued previously timed-out queries like query 17 and query 20, but both also cause significant regressions on other queries. Finally, we include a complete reproducibility package containing configuration files, source code patches, SQL scripts, workload runners, and CSV files. This slide summarizes the broader research landscape of automatic index advisors and shows how our project fits into that progression. Historically, the earliest work focused on classical optimizer-based heuristics. For example, Chowdhury and Narasaya introduced one of the first cost-driven index advisors, which later influenced Microsoft Database Tuning Advisor or DTA. Later, Valentin and colleagues developed the IBM DB2 advisor and introduced the idea of what-if virtual indexes. A virtual index is not physically created on disk. Instead, the optimizer behaves as if the index exists so that the candidate indexes can be evaluated efficiently without expensive physical creation. One of the most important classical methods for our project is extend. Proposed in 2019, extend uses a recursive greedy strategy to iteratively build multi-column indexes based on benefit per storage ratio. Later, the Magic Mirror experimental study compared multiple classical advisors and identified extent as one of the strongest classical baselines. More recent work shifted towards machine learning and reinforcement learning approaches. For example, Swirl used reinforcement learning with PPO, Balance extended Swirl using transfer learning, and more recently, LLMIA introduced a large language model based tuning free approach using the context learning. Unlike reinforcement learning methods that may require hundreds of training iterations, LLMIA typically converges within only 2 to 4 refinement iterations. The important research gap we identified is that many previous studies mainly evaluated optimizer estimated cost reductions rather than the actual physical query latency measured on a real database engine. Our project focuses specifically on measuring real end-to-end execution behavior. This slide explains an important methodological change we made during the project. Originally, our progress report 2 plan was to compare two reinforcement learning based advisors, Balance and Swerve. However, when we attempted to reproduce both systems, we encountered two major blocking issues. The first issue was with Balance. Although Balance was published in PVLDB 2024, the authors did not release a public implementation or artifact repository. Because this project category required us to run the algorithms end to end on a real database system, we could not include Balance without reproducible source code. The second issue was with Swirl. Swirl depends on TensorFlow 1.15 running in a Python 3.7 environment. However, the Apple Silicon's Rosetta 2 transition layers does not emulate AVX instructions. As a result, importing TensorFlow immediately crashed with an illegal instruction error. Recompiling TensorFlow 1.15 for ARM architecture was not practical because Google deprecated the build before official Mac ARM TensorFlow support existed. So we substituted Balance with LLMIA and Swirl with Extend. This still preserved the core spirit of the comparison, a modern learning-based advisor versus a strong classic baseline. This slide describes the experimental environment and methodology used throughout the project. One important point is that all experiments were run on real PostgreSQL database instances, not in a simulator. For the hardware environment, we used a 2024 MacBook Air with an Apple M3 chip, 16 GB unified memory, a Mac OS SQL 15.3. The database system was PostgreSQL 18.3 installed through Homebrew. We also used the HypoPG extension version 1.4.2. HypoPG allows PostgreSQL to create hypothetical and virtual indexes that exist only inside the optimizer for what-if planning. Both Extend and LLMIA internally rely on this capability to estimate index usefulness efficiency without physically building every candidate index during search. For the workload, we use the TPC-H benchmark at scale factor 1, which contains approximately 1.5 GB of raw data, 8 relational tables, and 22 standard analytical queries. The database was generated using the official dbgen tool, while the queries were generated using QGen. Because some TPC-H query syntax is not directly compatible with PostgreSQL, we patch certain query templates, mainly replacing the non-standard day 3 interval syntax with PostgreSQL compatible syntax. For measurement methodology, each query was executed 3 times consecutively, and we reported the median runtime to reduce noise for OS scheduling and caching variable. Each query had a timeout limit of 90 seconds. Most importantly, after each advisor generated recommendations, we physically created those indexes using create index and then ran analyze before rerunning the workload. This ensures that all measurements reflected actual physical query execution behavior. Finally, to maintain fairness, the workload, hardware, queries, and the measurement procedure remained identical across all experiments. The only thing that changed between runs was the index configuration. Before running either index advisor, we first established a clean baseline environment. The purpose of the baseline was to measure workload performance using only PostgreSQL's automatically created primary key indexes with no secondary indexes at all. This represents the untuned starting state that a DBA might initially inherit before any optimization work has been performed. Both LLMIA and Extend were evaluated against this exact same baseline configuration. For consistency, each query was executed 3 times consecutively, and we reported the median runtime. We also used a per query timeout of 90 seconds. To verify the clean baseline state, we used the PostgreSQL /di command shown on the right side of the slide. The output confirms that only 8 indexes existed, one primary key index for each TPC-H table. Another important methodological decision was that we did not perform warm cache pre-runs. This means the first execution remained a real cold run rather than an artificially warmed execution environment. This setup allowed us to evaluate the true impact of advisor generated indexes relative to a minimally indexed PostgreSQL database. This slide shows the actual workload behavior before applying any advisor generation indexes. Using only the 8 primary key indexes, 20 out of the 22 TPC-H queries completed successfully within the 90-second timeout limit. However, query 17 and query 20 both exceeded the timeout threshold and were recorded as timeout. This is a very important observation because it means that the workload was not merely slow, it was actually incomplete under the untuned baseline configuration. For the 20 queries that did complete, the total median execution time was approximately 6.78 seconds. The slowest successful queries were query 18 at around 1.44 seconds, query 9 at around 0.60 seconds, and query 21 at around 0.51 seconds. Most of the remaining queries completed in under half a second. This pattern is actually ideal for evaluating index advisors because the workload cost is dominated by relatively small numbers of expensive queries. A good query advisor should specifically target those expensive queries and reduce their execution costs significantly. The screenshot on the lower right side shows the actual PostgreSQL workload output, including the explicit timeout entries for query 17 and query 20. This slide explains the internal workflow of LLMIA, which is modern LLM-based advisor evaluation in our project. LLMIA was proposed in 2025 and is currently one of the most recent published LLM-based index recommendation systems. Unlike reinforcement learning approaches that may require hundreds of training iterations for each workload, LLMIA is designed to be tuning free. The core idea is to transfer database expertise into a general purpose large language model through in-context learning. In our case, the underlying model was GPT-4o Mini. The algorithm begins with a workload feature extractor. This component analyzes the SQL workload and identifies important columns used in bare clauses, join predicates, group by clauses, and order by clauses. It also extracts statistical information such as distinct value counts and table cardinalities. Next, LLMIA uses a demonstration pool. This is a curated collection of prior examples containing workload, recommended indexes, and refinement actions. The algorithm selects demonstrations similar to the current workload using Cousin similarity. Those selected demonstrations are then provided to the LLM as an in-context examples. Using those examples, the LLM generates an initial set of candidate indexes. Then LLMIA performs iterative refinement using database feedback. This feedback can come from estimated query cost using hypo-PG called LLMIA bracket C, or actual workload latency called LLMIA brackets L. In our project, we evaluated the cost instructed variant LLMIA because it is computationally faster and avoids the overhead of repeatedly executing the full workload during refinement. One important advantage of LLMIA is that it usually converges within only 2 to 4 refinement iterations, which is significantly smaller than the hundreds of iterations often required by reinforcement learning approaches. This slide describes the exact configuration we used for LLMIA along with the implementation patches required to run the published code successfully in our environment. For the LLM backbone, we used OpenAI GPT-4o Mini through the API interface. We evaluated the LLMIA variant, meaning the advisor used hypo-PG estimated workload cost as refinement feedback rather than repeatedly executing the full workload. The advisor performed 4 self refinement iterations with 8 candidate samples generated per iteration. For demonstration retrieval, the algorithm used cosine similarity, and we selected the top 8 demonstrations for in context prompting. We also used the storage budget proportion of zero point 0.5, meaning the advisor was constrained from recommending arbitrarily large index sets. To make the published implementation work correctly in our environment, we applied several patches. First, we modified the database connection setting to the point of our local PostgreSQL instance. Second, we changed the multiprocessing mode from spawn to fork. Third, we modified the SQL parser to split statements using semicolons instead of new lines. The original parser broke on multi-statement SQL files. We also patched compatibility issues related to PostgreSQL's 18's newer backslash directives that did not exist when LLMIA was originally published. Importantly, all batches were documented and included in our package. After 4 refinement iterations, LLMIA produced 14 create index recommendations and reported an estimated workload cost reduction of approximately 99.81% relative to the no index baseline. This slide shows the actual indexes recommended by LLMIA after the refinement process completed. In total, the advisor generated 14 create index statements. One clear pattern immediately stands out. The majority of the recommendations target the line item table. This is expected because line item is the largest and most workload intensive table in TPC-H, containing over 6 million rows. Overall, the recommendations appear quite reasonable and closely resemble the type of indexes an experienced DPA might manually create for TPC-H analytical workloads. This is important because it suggests the LLM successfully learned meaningful workload patterns from the in-context demonstrations rather than producing arbitrary recommendations. This slide shows the actual execution logs from running LLMIA and verifies that the recommended indexes were physically created inside PostgreSQL. On the left side, the log output shows the create index statements generated by the advisor during refinement. The log also reports the model's final estimated workload cost reductions, which was approximately 99.81%. According to the log, the best result occurred during iteration 3 out of the 4 total refinement iterations. After the advisor completed, we physically applied all recommended indexes using PostgreSQL create index commands. We then ran an analyze so PostgreSQL could update optimizer statistics using the new index structures. The screenshot on the right shows the PostgreSQL index catalog after index creation. We can see a total of 22 indexes, the original 8 primary key indexes plus the 4 additional LLMIA generated indexes. This step is very important because our evaluation was not based only on hypothetical and virtual indexes. Instead, the indexes were actually materialized on disk and incorporated into real query execution plans before rerunning the workload. This slide shows the actual workload results after applying all 14 LLMIA generated indexes physically inside the PostgreSQL. The most important result is that 22 TPC-H queries completed successfully. In particular, query 17, which previously timed out beyond 90 seconds, now completed in approximately 0.33 seconds. Query 20 also improved dramatically from a timeout to approximately 0.28 seconds. So the advisor successfully reduced the previously incomplete workload. We also observed improvements in other expensive queries. For example, query 21 improved from approximately 0.51 seconds to 0.27 seconds, which is roughly at 1.9 times speed up. The total measured workload runtime across all 22 queries was approximately 8.17 seconds. Now, an important point here is that LLMIA previously reported a 99.81% estimated workload cost reduction. However, the actual measured runtime reduction was much smaller. This difference highlights one of the central findings of our project. Optimizer estimated cost reduction do not directly translate into proportional real-world latency improvements. The screenshot on the right shows the actual workload output confirming all 22 queries completed successfully, and the final measured runtime was approximately 8.166 seconds. Most importantly, the number reflects the real measured latency using physical indexes, not hypothetical optimizer estimates.
Now I'll talk about the extend algorithm. This is the second algorithm we evaluated. Extend is a recursive greedy heuristic algorithm used for the index selection problem. This algorithm works in 4 steps. First, it starts with an empty index set, meaning no recommendations at all. Second, at each iteration, it considers two types of candidate moves. Either it can add a brand new single index or it can extend one of the existing index by adding one or more column to it. Third, every candidate move is scored by what's called a benefit per storage ratio. Next, it picks the highest scoring candidate and adds it to the chosen set. This process is repeated until no candidate exceeds the benefit threshold or until the storage budget is exhausted. So now let's look at the environment we ran, the configuration and the patches we made to the environment. First, on the left side, you can see our configuration. We tested extend with 5 different storage budgets, 500 MB, 1000, 2000, 5000, and 10,000 MB. The framework itself supports 19 out of 22 queries. It excludes query 2, query 15, and query 17. So we used only those 19 queries. On the right side, you can see that patches we made to the environment to make extend work on this. So first we added database named plumbing so that framework would connect to our existing TPC-H database instead of creating a new one. And next we updated the code and also modified the drop indexes function to skip primary key constraint. Now let me show you how we ran the output for this extend. So after dropping all the LLMIA indexes from previous experiment, we applied extend 7 index and ran analyze to update the optimizer statistics. So we reran the same 22 queries that we used in previous algorithm, but we ran 3 runs per query to report the proper median. So the figure shows us the index list after extend 7 index were created. The total you can see here are 15 rows, which have the 8 primary keys index and 7 new indexes from extend. Next, these two figures shows us the how the actual workload ran. The output is divided into two images. In the first image, you can look it ran from query 1 to query 14, whereas in second image it ran from query 15 to query 22. So all the 22 queries have been executed in the time 10.194 seconds, as you can see below. So let's look at the extend run results. Here all 22 queries succeeded, which is same as LLMIA. Both timed out queries from the baseline, which are two queries, query 17 and query 20, have been rescued. Here query 17 finished in 0.30 seconds, which was previously was timing out. Next, query 20 is finished at 0.17 seconds, which is slightly better than the LLMIA, which 0.28 seconds. The total number of indexes after applying extend recommendation here is 15. That is 8 primary keys, 7 new index created from extend. So this coming into this table shows us the main side-by-side comparison of all three configuration. Here the baseline with only 8 primary key indexes succeeded on 20 out of 22 queries with a total time of 6.78 seconds, whereas when we used LLMIA, it succeeded on all 22 queries, that's 8 primary keys and 14 LLMIA indexes in just 8.17 seconds. Next, when we ran extend algorithm with 15 indexes and 8 primary keys, it also successfully ran all 22 queries, same like LLMIA, but in 10.19 seconds. The bar chart shows us so to conclude this project, here we fully presented a end-to-end comparison of two index recommendation methods. Here we used both algorithms and they were run against a PostgreSQL database and we applied the recommendations as physical indexes. Next, some of the key findings we found here were first, both algorithms successfully ran the two queries which were timed out before. These were query 17 and query 20. Next, the per query analysis showed a no free lunch trade-off, meaning both algorithm earned some queries by an order of magnitude, which is very little. Here, LLMIA hurts query 4 by 12.3 times, whereas extend hurts query 7 by 8.9 times. Next finding is the algorithm choice depends on which queries dominate your workload. So next, if you look at some of the limitations, first, it is single benchmark, meaning we evaluated only on TPC-H scale factor 1. But if we use larger scale factors, the results might look different. Second limitation is we used only single PostgreSQL, but a newer version and other versions might give different values. Uh, Next, this is a single classical heuristic. Means here we evaluated only extent. The full LLMIA paper compares against 12 baselines, which gives different values. Next limitation is that we evaluated only the cost instructor variant LLMIA C. We did not run LLMIA L, which is latency instructed variant. And lastly, we ran this on our Apple M3 chip. Results on other hardware or larger memory configuration may differ. So some of the future work which can be done here are first to test on TPC-DS and job benchmarks at larger scale. Next, test workloads where one query type dominates to see if the no free lunch pattern still holds the optimal index configuration. Next, build a hybrid algorithm. It could be a system that uses extend as a starting point and LLMIA as a refinement step. And next, these are the 10 references that we have selected. Thank you. Now let's look at the demo. So now we'll tell how this demo works. So first we will connect to our PostgreSQL. So now we have connected to our PostgreSQL. Now let's look at all the indexes which are currently in this database. So you can see exactly 8 indexes. One is the primary key per TPC-H table. There are no secondary index here. So let's come out this. And now let's run our baseline workload script. So now I'm running our baseline workload script. Let me tell what's happening here. The script runs all the 22 queries, and each query is executed 3 times back to back. But one problem here. So almost all the queries execute except 2 queries. One is a query 17, one is a query 20. These two doesn't execute, and there's a timeout message which will appear. Now let's look at the timeout message which will appear in 30 seconds. So as you can see, we can see the timeout for query 17, meaning the query 17 did not execute and it timeouted after 30 seconds. The same thing will happen for the query 20 also. So as you can see, the query 20 also have been timed out, same like query 17 after 30 seconds. So looking at the summary below, we can see only 20 out of 22 queries executed with around median of 8.93 seconds. So this is our baseline. Next, I'll show you what LLMI recommended. So we ran this LLMIA against our database, and here are the 14 create index statements that LLMIA gave us. The 6 indexes are on line item, the largest table, whereas 3 are on orders and 2 each on customer and supplier. Next, I will apply all these 14 indexes by piping the SQL file into PSSQL. So here each create index build the actual index. This takes a few seconds because some line items cover a lot of rows. So this has been executed. So now let's see all the 22 queries. So these are the all the 22 queries that we are going to execute next. Here there are 8 primary keys plus 14 new ones which we have created. Now I will rerun all the 22 queries that we have previously rerun, wherein previously we the two queries did not execute, query 17 and query 20. But now we are rerunning the all the queries, but those two queries will execute. Watch query 17 and query 20. Now they should execute and they should under a second. And here the queries are executing much faster than the baseline queries. So as you can see that the query 17 is also have been executed and query 20 is also executed. So the summary we can see is that all the 20 queries have been executed and the median is around 6.9 seconds, which is a lot slower than the our baseline. So next we'll go to extend, but before applying extend recommendations, we need to drop all the LLMIA indexes for a clean comparison. First, let's drop all of the LLMIA index. So this little block iterates through every index and it drops it. Now let's come out of this. So now we will run the. Now let's look at this extend algorithm, which is the second algorithm that we have used. So first, let's let's run this, which shows us the how many create index statements that are there. Here we have only 7 create index statement, which is half as many as LLMIA. Now I'm applying these 7 create index statements. Next, after applying this, I will verify using the \di, which where I should see 15 in total. Now I will verify that if so as you can see, we we see a total of 15 rows, which has 8 primary keys plus 7 new things that we have created. Next, let's run this in the same workload, same methodology with all the 22 queries. So here all the 22 queries will be run. Even the query 17 and query 20 should also be run using the same workload and same methodology. So in this, the query 17 and query 20 will also be run unlike in what happened in baseline. As you can see, query 17 has been run. Same thing will happen to query 20. So from the summary, we can say that all the 22 out of 22 succeeded with a total median time of around 8.4 seconds. So now let's compare between these two algorithms. So here is the comparison. In the baseline, only 20 queries have been executed, whereas in LLMI, all the 22 queries, in extend also all the 22 queries has been executed. But the medians are different. Like in the baseline, even though only 20 queries have been executed, the median is 8.9, whereas in LLMIA, even though all the 22 queries executed, the median is 0.69, which is less than baseline, whereas in extend, it is 8.4. So now let's look at the comparison of these three. So here are the 22 queries and all the three algorithms, baseline, LLMIA, and extend. So, and here also we can see that how faster, how slower the each query is. Like if you look at query 4 in the baseline is around 1.1 seconds, whereas in LLMIA it is 0.09 and extend is 0.1 second. Whereas in query 7, extend is takes much more time to execute. Whereas in other queries such as like query 19, or you can look at query 18 where extend executed much faster than both baseline and LLMIA since it's half the time.